morning time with Cunningham, teaching physics the best that he can. It's morning time with Cunningham, join along if you can. It's morning time with Cunningham, teaching physics the best that he can. Join along if you can. It's morning time with Cunningham. Alright, good morning AP Physics. So I have a little stupid intro that I recorded a lot of time making. Stupid. It took me like a lot of time to figure out how to do all of that, and how to like record it where I could record over myself and not have like the video lag and have it do it the right way. So that took a lot of stupid time for a very stupid short payoff. So just know that is the kind of level of effort you can expect moving forward. Yeah. So you probably didn't enjoy that, but just know that I'm gonna come up with a little intro that I'm gonna put in front of all my videos, and maybe I'll change it. But for right now, it's gonna be morning time with Cunningham. So there you go. Not really the point. So yeah, this week make sure that you are catching up on everything. You should be going through the FRQ that's like 2 weeks ago, and then last week you should have gone through all of the multiple choice questions. I did not really receive any questions this week. I would answer those questions here if I could. I don't know what you need because I didn't really hear a lot from you. I did meet with a few students, and I answered their questions, but I did that when we met, so it's not necessarily a thing where I know what to cover for you guys. If you have finished everything this week, when you contact me, I will give you the additional thing I want you to do. If you already contacted me, you know that. I said, hey, here's this thing I want you to do. It's not a lot. I think it's going to help you out a lot moving forward. If you have not finished everything this week, you still need to contact me, but the thing that I want you to do is to contact me and get caught up on your other work. The thing that everyone else is doing, I'm probably just going to have you like fit that in over time as we do the rest of it, but just don't worry about it right now. I do want you to get caught up with everything else. So that's the first multiple choice section, the FRQ, and there was questions that I made up that went along with that, so make sure you do that as well. And then last week was just multiple choice questions for angular momentum and torque and all that kind of good stuff. So yeah, just make sure you're going through and doing that. The main thing I would suggest is just start being familiar with a few things, and it's really pretty straightforward. We're doing a lot of stuff with kinematics, so this is a good time to review that. So we're just talking about things that have a really similar linear equivalent, and I probably already did this, but that's fine. I don't mind. And theta, which is x. So you really just need to be starting familiar with this stuff when it comes to angular kinematics, and it just means that all of these things have an equivalent. So this omega, which looks like a W but is actually a Greek O, this omega is basically velocity, except for what's the velocity in terms of my rate of spinning. This alpha is A, or an acceleration, which is, again, how much is my speed changing, but in this case in terms of how fast I'm spinning. And then theta is my displacement, or x. In this case, again, theta is in terms of spinning. How many rotations have I completed in terms of radians, right? So all of these things are going to be in terms of radians, because that puts it in terms of what's the rate at which this thing is spinning, how many rotations does it make, right? Not in terms of like how quickly is it going, right? That would either be these velocities, or you could take these angular velocities and multiply them by their radius, and that would tell you essentially these objects here. But again, that's the main difference. Is it's not necessarily how fast they're going; it's what's the rate at which they're spinning, right? So the other things to take a look at, and they're relatively straightforward, and I'll just cover them all in this video. It's no big deal. Is this formula? This is your formula for torque, and here we have tau is equal to FR sine theta, and that's this symbol here is tau. It's like another Greek letter. Yeah, and so tau represents our torque, and it just tells us that torque is the force an object has applied to it times the radius away from its axis of rotation times the angle at which that's applied. And what does that mean? Well, that's actually relatively easy to show. So let's say I have a wheel, and let's say this is like a giant valve, like you would open steam valves with, kind of thing. And so let's say that I'm going to hook like a wrench to the center of it because I want to move it. Right. So let's say I have this thing. I have a circle. It's like a giant valve. And again, I have this wrench attached to the center because I'm going to like try to move it. So essentially what torque is saying, what is my rotational force? How much of the force that I apply to this thing is actually going to go into rotating it, right? What's the strength in which it rotates? And this thing's going to have a natural resistance too, kind of like friction. In fact, it may even be friction, but it'll be rotational. So we may have some things that we have to overcome in order to even get it to turn, right? So in other words, let's say that if I don't apply at least 200 Newton meters of torque, then this thing won't turn at all. Well, that's the same thing as saying this bench won't move if I don't apply at least 200 newtons of force, right? So it's essentially the same idea. So we have this again, tau, torque, which is represented by the force. So I'm going to push on this thing, right? Let's just go ahead and draw that. I'm going to push on this thing, right? And we all know that how hard I push on it is going to matter in terms of whether or not it's going to move, right? And so that is going to be the F portion, right? So we have here, again, tau is equal to FR sine theta. So F is the how hard am I pushing, right? Cool. So that is the F, how hard am I pushing? The next thing, the R, is this radius. And it's how far away are you from this axis of rotation? This thing rotates around this dot. That's its axis, right? And so the R is just like saying, and I'm going to use a different marker color for this, just because I think it's easier. The R is another way of saying, what's this distance, right? How far away am I from that center of rotation, right? And then the theta is what's the angle I'm applying this thing at. Between the R, between this lever and my force, what's the angle between them? And what you'll know is that sine 90 is 1, which means that at 90 degrees here, right, if that was a perfect square the way that I drew it, at 90 degrees, all of my force is going to go into pushing this thing rotationally, which is what we'd want. And it also would show you that if I have a longer lever, that my torque is going to go up. That's the thing that you probably already know, but you should know, is that longer levers help us turn things more easily, right? So if we were to have, for instance, let's say like a seesaw, right? Let's say we have a seesaw. It's easier to push things up and down on this side than it is on this side because of the length, right? So if something is like really, really close to this object, again, it makes it a lot harder for them to push the thing and pull it upside down. Let's say we put a really heavy weight on this side. The longer that this lever is, right? Let's say we put a little weight on this side. The longer that this lever is, the easier it becomes to push and pull this thing upside down. This guy named Archimedes, he's an ancient Greek, said that if you had a lever long enough, a single person could lift the entire earth, right? Because of this exchange of force. So again, that's what torque really means. I'm going to rotate this thing, right? What's the angle here? That's my theta, right? And think about when you go to push a door. When you go to push a door, you push it flat against the surface, you push it away from the hinges, and you push as hard as you need to. Obviously, if you need to push harder, you just keep pushing. But you don't ever push it really close to the hinges because that radius would be really small, and you don't push it like at a weird like sideways angle. Let's put it this way. Let's say that this flat surface here, this 90-degree surface, was the door. Like I want to push on it like 90 degrees, right? I don't want to push it like this. Like I don't want to try to do that. And you know that because again, you've opened a door before in your life. Let's say the other concept of this chapter. One of the other concepts of this chapter is this idea of angular momentum, right? So we have this idea, angular momentum, which is my angular momentum is my moment of inertia times my angular velocity, right? Well, think about this as being the same thing as P is equal to mv, because they basically are. So my moment of inertia is another way of describing how do I resist this motion. Well, in linear motion, your mass is your inertia. That's the thing we covered earlier in the year, right? Mass is inertial mass. It is inertia. And so that is, in linear momentum, how I resist changes to my motion. Well, moment of inertia is how do you resist those changes when you are talking about spinning something, right? So let's say that you have like a simple rod, and it's going to spin around this, right? Well, that's going to have a certain moment of inertia or resistance, right? Well, how the weight is distributed around this center is also going to affect that, right? So let's say I put two big weights on the edge here, right? I put two big weights on the edge. Well, that's going to change my moment of inertia. It's going to make it harder for me to get this thing moving, but it's also going to make it harder for me to stop it from moving once it is moving, right? And that's, again, because it's going to have all this weight that's on it while it's pushing around. It's going to have all this different inertia. So that's what your moment of inertia represents. It's exactly like talking about your regular inertia in linear momentum, right? We have this inertia and we have this moment of inertia. Now in physics, we have this thing called a moment, and a moment, just to define it, just is any physical quantity and it's like distance from an origin, so to speak, right? That's what the word moment means. So here we have moment of inertia. Well, mass is going to be our physical quantity, and then our distance from our origin is really going to be saying, like, how is this weight arranged around this center? How far away is it? What's the shape of it? And so therefore, that's where we get this term, moment of inertia, right? Cool. And so then obviously we see the relationship between velocity and angular velocity. They're the same basic concept, right? So when we talk about angular momentum and we talk about linear momentum, we're talking about those two ideas. Cool. And so we do have a standard equation for what my moment of inertia is. I equals mr squared. You do not get this on the AP physics formula sheet, as far as I can tell. And they, as far as I can tell, do ask you questions that refer to you understanding this, right? This changes, this I equals mr, based on the shape of the object. This is like the standard for like a normal rod. They may change that, but they should give you the formula if they change that. I'm telling you, I've worked on some problems in this where they don't give you the I is equal to mr squared, but they expect you to know it. So just make sure that you're taking care of that. And the only other concept that we need to make sure is the same. We have this concept of conservation of momentum, this idea here. We have this idea that my momentum beforehand has to equal my momentum afterwards. Well, that's the same thing as my linear momentum. So if I'm not spinning, I can't just start spinning without offsetting momentum. In other words, let's say I go to push myself off this desk to spin in this chair. Well, technically, I am applying the exact opposite momentum to the table. Now, the table doesn't move because it has other forces and other things that are being applied to it. But in order for me to get this offsetting momentum, I have to have some other angular momentum, right? Something else is going to spin to offset that. Kind of like when I go to throw a ball, right? I can't just get this momentum to the ball. There is this offsetting momentum to the ball. Now, do I fly backwards? No, because there's other forces like friction on me. That's really what the main ideas that I can see that you need to make sure that you understand. Yeah, there's I mean, a lot of stuff that they cover in this chapter, if I'm being honest, but those are the main ideas. And then this idea called rotational equilibrium. Rotational equilibrium is really easy. It's when all my rotational forces cancel out. So I'm not accelerating at all in my spinning, right? That doesn't mean I'm not spinning. It just means that I'm not accelerating in my spinning. The same way that an unbalanced force causes an acceleration, an unbalanced rotational force, or torque, will cause some sort of rotational acceleration, right? Now, if those forces offset each other, then you're going to go at a constant speed, which means that you are at some sort of equilibrium, right? So if you're not spinning, then obviously all the forces on you cancel out. If you're spinning at a constant rate, then all those rotational forces obviously cancel out. And so in this case, you can see that it's really the same concept. So just make sure that when you're looking at all this stuff that you recognize that. That's kind of the stuff that I'm going to cover as a brief overview. Just make sure that if you have any other questions that you let me know. And again, we have office hours a day between 10:30 and 11:30. You do need to contact me. That's probably the best possible way to do that, if I'm being honest, but that doesn't mean that you have to join me. In fact, you might not see this video beforehand. It's almost 10 o'clock. Stop it now. I'm going to try to post it before then and get it out to you, and then hopefully see you at 10:30. So just let me know, and thanks.